very good afternoon to all of you. Today's lecture is on land surface temperature studies in urban areas. Now, we all know about air temperature. We all know that there is an ambient air temperature around us, but probably we have never thought that there is something called land surface temperature also. So, the surface materials possesses certain qualities, and based on those qualities, we have the surface temperature for those surface materials. So, let us understand what land surface temperature is and what it is dependent upon. So it is dependent upon several factors and the premise lies in thermal remote sensing. So let us understand thermal remote sensing and why LST is important. Land surface temperature in short will be called as LST in the lecture, so kindly understand. Okay, so what do we understand by land surface temperature? So land surface temperature is the skin temperature of the ground, and ground is made up of certain materials. For bare soil surface, the LST is the soil surface temperature. When it comes to dense vegetated ground, then LST can be viewed as the canopy surface temperature of the vegetation. So LST in remote sensing is defined as the average surface temperature of the ground under the pixel scale mixed with different fractions of surface types. Now, if you recall in my last lecture, we had talked about the spatial resolution. So each pixel is made up of various land uses or land covers depending upon the size of the pixel. So if you assume that one pixel size is there and one pixel is made up of various land covers, then the surface temperature for that pixel will show you the surface temperature of all the mixed pixels. So the average temperature will be shown to you. Now, why are we understanding what is land surface temperature and why are we studying land surface temperature both at global level as well as local level? So it is important because we all know that the climate is changing. So climate can be attributed to various atmospheric factors as well as the surface factors. So there is an interaction between the ground as well as the atmosphere. So this interaction has to be studied with the help of two phenomena: the ambient air, the wind around us, the ozone that is in the atmosphere, the carbon dioxide that is there, the water vapor that is there. All this can be studied and this becomes a vertical profile that is in the atmosphere. So all this is studied with the help of atmosphere sciences. Now when we come to land, the surface studies are referred to as the surface parameter that we are studying can be referred to as land surface temperature. So these two interactions will give us the idea that what is the climate change taking place and how it can be helpful for analyzing the climate pattern in the future. We also am talking about the urban studies. Now how LST can be helpful in urban studies? The urban materials have certain qualities. Urban materials are made up of certain chemical composition. So all these urban materials have a certain tinge or proportion of several materials integrated together. And all these materials have a specific chemical composition and they have their own kinetic temperature. So we need to understand that how each and every material behaves and what is its surface property that gives it a warm texture or a cooler texture. LST is an important requirement in creation of climate models. Yes, when we are, as I said, that climate studies are important and in the similar way climatic models are important. When I say climatic models, it simply means that understanding today's scenario of the climate and forecasting that what can be the probable in the times to come, in the future in general. Land surface temperature is a good indicator of the energy equilibrium of the Earth's surface and the greenhouse effects. I mentioned that the atmosphere is made up of various gases. The atmosphere in itself is divided into several layers. So all these layers in itself is comprising the atmosphere which has greenhouse effect and the Earth's surface. Now both the interactive surfaces between the Earth's surface and the atmosphere, we have to understand how the energy equilibrium is taking place. Now when I say energy equilibrium, what I mean to say is that there is radiation coming, short wave, long wave radiation to the Earth's surface. I will explain in future, in the future slides, that what do you mean by short wave and long wave radiations. So when radiation comes to the surface, it hits the surface but travels through a medium. And the medium is what? The medium is atmosphere. So we have to understand that what is taking place in the atmosphere, how much attenuation is taking place in the atmosphere, what is hitting the surface, and what is going back again, passing through the atmosphere and reaching the sensor where it captures the pixel value in the form of DN values. Then land surface temperature is a key variable and helps in controlling the fundamental biospheric and geospheric interaction between the Earth's surface and the atmosphere, as we have already discussed. Then when we talk about urban areas, as I said, material have certain properties and it can be estimated using land surface temperature. So we have already read about something called urban heat island effect and urban cool island effect. Those who don't know, I would like to make them understand that what is an urban heat island effect. Heat island, when I say, that means the area is behaving like an island and a heated island. So when urban heat island effect, immediately what comes to our mind is urban areas. Since urbanization is taking place, concrete jungles are emerging. So all the urban areas are behaving as trapping the heat in itself and making the surface temperature too high. So we regard that urban heat island effect is very predominant in urban areas. So it is important to understand that how much is the urban heat island effect predominant in a particular city, and it can help in understanding that we all know that vegetative cover helps in reducing the ambient air temperature as well as the surface temperature, and the water bodies does the same. So it can be helpful to planners to understand that the surface temperature is rising within this area. This area has less green space, this area has less water body for the so that the heat is not getting it is not moving out and it is getting stuck in the same concrete jungle. So we need to plan accordingly and plan in such a way that green spaces help in maintaining the surface temperature as well as the ambient air temperature. At this point, I would also like to mention that air temperature and surface temperature both have close interrelation with each other. Then effect of land use on the atmosphere. We have already discussed this. It is helpful in estimating long wave fluxes or indirectly as when estimating latent and sensible heat fluxes. What is a long wave radiation? More than 4 micrometer. A short wave radiation less than 4 micrometer. So we will study all these concepts in detail in my slides to come. Then very important function of land surface temperature can be in the estimation of soil moisture. Now we all know that in hydrology, soil moisture is very important. We need to understand the soil texture and understand the soil moisture. Moisture because the various patterns that how water water evaporates or water penetrates through the pores of the soil dependent upon the size of the soil particle, etc. So it is helpful in estimation and further it is helpful in drought assessment. Then land surface temperature is one parameter which can be helpful to understand along with soil moisture the other parameters of for drought assessment. Other climatic, hydrological, ecological and biogeochemical studies. We will discuss in detail that where it is used the most. So now let us move and narrow down to understand that why we are concentrating on thermal remote sensing to understand the land surface temperature studies. Now as we all know that remote sensing has been divided into three broad parts, which are visible reflected infrared, which works on the principle of reflectance of the radiant energy. The range is from 0.3 to 3 micrometer. Second part of the electromagnetic spectrum gives you the thermal infrared, the thermal radiation principle it works on. It actually works on the kinetic energy of the surface. And the range is 3 micrometer to 14 micrometer in general. Actually, the thermal infrared or the thermal remote sensing, the range is considered to be 3 to 35 micrometer. But 3 to 14 micrometer, why we have written? Because this is the in the slides to come you will understand, but still 3 to 14 micrometer is the area where less of attenuation is there, and this is the area where analysis can be done most promisingly. Third is microwave, which works on the backscattering principle. I'm sure everyone knows about microwave remote sensing. 1 millimeter to 1 meter is the range. So we today are focusing on thermal infrared and hence understanding the thermal remote sensing for estimation of land surface temperature. So land surface temperature is a product which can be done through a tool called remote sensing, through a algorithm, various algorithms which we will discuss, and the principle behind it will be thermal remote sensing. So we know what happens in thermal remote sensing. Satellite is there to take or capture the data from the surface. So there is the radiation coming to the earth, the incident solar radiation. It strikes all the features of the earth uniformly after the atmospheric attenuation. Remember that, because our atmosphere is made up of various layers, various levels. So atmospheric attenuations take place within this within the incident radiation. After the attenuations, the incident radiation reaches the surface materials and then it moves back or is reflected back. Reflected solar radiation is trapped by the satellite and it gives you the value of the per pixel DN. Again, in thermal remote sensing, what happens? The atmospheric, the atmosphere has no role to play, because it works on the principle of not reflectance but the kinetic temperature. So what will happen is all the surface properties will have certain radiation, and that will be the emitted thermal radiation. So in thermal remote sensing, we are focusing on the emitted thermal radiation. And this emitted thermal radiation is dependent upon the character of the surface, and that factor on which it is dependent is known as emissivity. We will read about all these topics in the slides to come. So thermal remote sensing picks up the radiant emitted energy from a surface target which is heated through. Obviously, it is not dependent upon the reflectance, but it is getting heated because of the sunlight. So how it is getting heated, or how the surface property will change, or how it is going to emit, based on three factors, that is radiation, convection and conduction. Now radiation is the heating of the surface material. Convection is atmospheric circulation and conduction is through the ground surface. So as I discussed that there are two types of remote sensing, reflectance remote sensing and emitted remote sensing. So in reflectance remote sensing, which is dependent upon the solar radiation, the characteristic property is reflectance of the surface and changes with different wavelengths. In thermal remote sensing, characteristic property is how well the energy is emitted from the surface at different wavelengths. Thermal remote sensing does not depend on the reflected light, as I told, so it can be done at night also. Example here is that MODIS. MODIS is a satellite sensor. It gives you the product both aqua and terra. It gives you the product of night time also and daytime also. Now, when we were talking about long wave and short wave radiation, we were talking about thermal remote sensing. We have discussed that thermal remote sensing is from 3 to 14 micrometer or maybe till 35 micrometer. However, the visible or the reflected area was 0.3 to 3 micrometer. So in general, we can say that reflectance remote sensing uses the short wavelength in the visible and the SWIR band. The SWIR area, SWIR means short wave infrared. But on the contrary, the thermal remote sensing is towards the higher wavelength. So the Earth radiant temperature is dependent upon two major factors, temperature and emissivity. Excuse me. Temperature is ground surface kinetic temperature, which depends upon the heat energy budget and the thermal property of the material. And emissivity is the property of the material controlling the radiant energy flux, and it depends upon various factors like color, surface roughness and the surface state of the object. In detail, we are going to discuss the emissivity. Now, when we were talking about the visible spectrum, the thermal spectrum and the microwave spectrum, you can see in the electromagnetic spectrum, the visible is from 0.4 to 0.7, reflected infrared is from 0.7 to 0.3, which together is the visible reflected infrared 0.4 to 3 micrometer. After that comes the thermal infrared, the active thermal area, that is 3 to 14 micrometer, and beyond it then microwave starts. Now, within the electromagnetic spectrum, there is something called atmospheric window. Atmospheric windows are those windows which have less effect of the atmosphere, less effect of the atmospheric attenuation, which takes place due to water absorption, water vapor, ozone, carbon dioxide, because these elements absorb. So the atmospheric windows are those regions that help in passing through the energy. The absorption bands, regions that absorb most of the infrared energy. Remote sensing devices detect infrared energy in these regions because the atmosphere allows a portion of the infrared energy to be transmitted from the terrain to the detectors, and the attenuations are least. So now summing up, thermal infrared is in terrestrial remote sensing, a region of 3 to 35 micrometer is called thermal infrared. Least spectral absorption takes place in the atmospheric window. So it is helpful that for all remote sensing applications and for data acquisitions, we use such an area that has least spectral absorption. Then within the thermal infrared, the excellent window that is available to us is 8 to 14 micrometer, as we have already discussed. The poorer windows lie from 3 to 5 and 17 to 25 micrometer. Beyond that, it has not been explored so far and not much of work has been done. Now it is essential for us to understand the physical laws that govern land surface temperature estimation. There are three laws which I am going to demonstrate right now. The three laws are Planck's law, then Wien's displacement law and Stefan-Boltzmann law. It is important to understand the principles of these three physical laws. So first law is Planck's law. Planck's law tells that amount of emitted energy per wavelength is dependent upon the object temperature. So if we see that the sun will have very high temperature and at a shorter wavelength, as you can see in the graph, whereas the average Earth's temperature is 300 Kelvin towards the longer wavelength. So in the graph, if you see, the x-axis is from 0.1 to 100 micrometer, and as you can see that the Earth, the wavelength, the average wavelength is 9.7 micrometer. So for Earth, the average at which the Earth's temperature can be measured is 9.7 micrometer. So we can easily understand that from within 3 to 14 micrometer, all the elements on Earth can be measured. Wien's displacement law. Wien's displacement law tells you that the wavelength is inversely proportional to the temperature. So it says that for colder surfaces, compared to that of sun, Earth is a colder surface. So the colder surfaces, the peak of blackbody curves moves towards the lower wavelength. We have already seen this phenomena in the last graph. For Earth, the wavelength was higher and the temperature was comparatively lower, that is 300 Kelvin. The average surface temperature, it is actually not 300 Kelvin, it is 297 Kelvin, but generally we relate it to 300 Kelvin. Then for example, and for hotter areas, then the wavelength will be a little lower, on the lower end. Supposedly, now where this Wien's displacement law can be useful is that there is a forest fire of approximately 1000 Kelvin. So you know that you will have to refer to a band with a wavelength of so and so micrometer. In this case, 2.9 micrometer. Depending upon the formula, lambda max is 2898 upon T. 2898 is a constant. So you can easily understand that for a certain temperature, you know about the kinetic temperature of the surface material, you can easily find out that at which lambda or at which wavelength that object can be identified within thermal remote sensing. Now why I am saying this is because certain sensors have different breakages of wavelengths, like Aster has of 4 bands of thermal, then Landsat 8 has 2 thermal bands. So which band to use and which not to use, 8 to 10, 10 to 12 micrometer, which you have to use, you have to decide. Landsat is giving you 8 to 10 and 10 to 12 micrometer, 2 windows, 2 thermal windows. Third is Stephan-Boltzmann law. So Stephan-Boltzmann law is going to tell you the relationship between the surface temperature and the total radiant temperature. So the total radiant temperature is 4 times of the total radiant temperature is the surface temperature. So what it states that colder targets emit only small amount of electromagnetic radiation, and Wien's displacement law predicts that peak of the radiation shifts towards the longer wavelength when the target is getting colder. So even colder surface will have less wavelength. Thermal remote sensing deals with small amount of low energy photons, and hence its detection is difficult, as we all know that less energy at higher wavelength. So its detection will be very difficult, and this is the reason why we have not been able to develop strategies based on which we can have higher resolution thermal remote sensing data available, so that we can work on other areas where high resolution satellite data is required for thermal remote sensing. So at present, the best resolution that we have, spatial resolution for thermal data, is resampled 30-meter data from Landsat. So Landsat can be used. So we have to sometimes compromise on the spatial resolution so that the signal to noise ratio is not disturbed. Now we have to understand the principles, 2 principles of black body and grey body. What is a black body? A black body is a perfect absorber, perfect radiator, but in all wavelengths. So it is ideal in nature. But black body is a myth. Nothing can be a black body. So there comes a concept of grey body and selective radiators. So grey body, materials that absorb and radiate at a certain fraction as compared to that of a black body are grey bodies, and the fraction is constant for all wavelengths. However, in selective radiation or selective radiators are those that radiate at a certain wavelength, while on the others they don't have that phenomena. So you understand by the word itself, selective radiators. Most of the materials on earth will be what? It will be selective radiators. So this graph explains the selective radiator as well as the black body as well as the grey body. So grey body, you know that by a certain percentage it is reduced, black body is very ideal. similar at all wavelengths. However, selective radiator shows you the actual scenario that yes, certain materials have certain property in certain wavelength and different in the other. So we were discussing about two premises of thermal remote sensing, the temperature as well as the emissivity. So temperature we all know, but emissivity we don't know probably. So we will understand what emissivity is. So the fraction of energy that is radiated by a material compared to the black body is referred to as emissivity. Now this is a definition. So energy that is radiated by the material compared to that of a black body in relation to that of a black body is referred to as emissivity. Now when I say this statement, you can easily understand that I am talking about a fraction, and when I am talking about a fraction, we can now conclude that emissivity is going to range between 0 and 1. Now, there is a strong relationship between two terms called emissivity and reflectance. So, there is a law that states and describes this relationship between the emissivity and reflectance. Now, why I am bothered about reflectance is because in the visible region, we are concerned about reflectance. So, if we know the reflectance properties of the surface, we can somehow understand about the emissivity part of the material. So emissivity measurement is difficult on the ground. However, spectrometers can be used for the reflectance measurement. So what Kirchhoff's law is going to tell us is that objects that reflect well have poor ability to absorb or emit, and vice versa. So how we can understand this? In general, we say 1 minus reflectance will give you the emissivity, and vice versa for the earth materials, for the surface materials. So we can see that at different wavelengths, the emissivity ranges for sandy soil and marble. Kirchhoff's law again says that good absorbers are good emitters, good reflectors are poor emitters. So how I am going to relate this, please see. Good absorbers and good reflectors. So what are good reflectors? Good reflectors like the tin surface on the industrial shed. They have very good reflectors. So that means the emissivity factor is going to be very, very low there. So let us see. Yes, it is like that or not. So emissivity, as I said, is going to range between 0 and 1. It is going to fluctuate depending upon the wavelength of energy being considered. Then a grey body less than 1 at all wavelengths because a certain fraction is reduced as compared to that of black body. Now, what is the range 0 to 1? So all materials will have some range from 0 to 1, which will have high, which will have low, we will see here. Distilled water will have very close emissivity, very close to 1, 0.99. Others like polished aluminium, stainless steel and the tin surface, very good reflectors, they will have very less emissivity. Emissivity can be calculated from the satellite image, and don't worry about that, we are going to discuss in the future slides. As I said, emissivity is dependent upon various factors. So what are those factors? Color. Dark colors are good absorbers and emitters and have high emissivity. Surface roughness. The surface roughness is another important parameter. Greater the surface roughness of an object relative to the size of the incident wavelength, the greater the surface area of the object. So this way, emissivity is dependent upon color and surface roughness, but there are more parameters. So let us see what more. Moisture content. More moisture of an object, greater its ability to absorb and become a very good emitter. So a moist soil will have good emissivity. Then compaction, the degree of compaction, the field of view, the emissivity of the single leaf will be different from that of a bunch of leaves, and obviously it is wavelength dependent. Emissivity is absolutely wavelength dependent. So right from the beginning of the presentation, I have been talking about radiant temperature and kinetic temperature. So radiant temperature, reflectance, okay, that can be measured with the help of radiometers. Kinetic temperature measured by direct contact, and radiant temperature is remotely measured. So kinetic temperature can be measured with the help of direct contact only, but radiant temperature can be measured from the satellite also. So radiant temperature is dependent upon emissivity, kinetic temperature, thermal properties and rate of heating. Now what is the relationship between kinetic and radiant temperature? Let us see that. Radiant temperature is the brightness temperature of the surface. Kinetic temperature is the surface temperature of the natural object. So there is a relationship between the radiant and the kinetic temperature, and it is by a factor of emissivity. As you can see, kinetic temperature is radiant temperature upon epsilon, that stands for emissivity, to a factor of 1 by 4 to the power of 1 by 4. So yes, kinetic temperature will remain constant, however the radiant temperature will keep on changing and it can be sensed by the sensor as well. So certain materials behave differently at different wavelengths. We have seen. So at short wave and long wave radiation, short wave means what? Till 4 micrometer. So in initial part of the day, the short wave radiation works and it is going to absorb the radiation, and the long wave radiation after 4 micrometer is going to work. So all the materials on the earth is going to absorb and retain the heat. So what are the satellite products that are available for land surface temperature estimation? As I told you, MODIS, Aster, Landsat, Severi, Kalpana, Kalpana is Indian, INSAT, INSAT 3D, FY2C, out of which Indian is Kalpana and INSAT. But the only problem with these two sensors is that for land surface temperature studies within the urban areas, we cannot use them because the resolution is in kilometers, 1 kilometer, 4 kilometer and 8 kilometer. It is helpful in global studies. So if you are interested in a regional study or a state level study, then you can use these products. If you are interested in urban studies, then the best possible is of Landsat, which is at resampled 30 meter spatial resolution. Freely available, thermal. So number 6 band, thermal band number 6 in Landsat 5 and Landsat 7 is thermal band, and for Landsat 8, 8 to 10 micrometer and 10 to 12 micrometer, 2 bands are there. 9 or 10, 10 to 11, you may check once. These are the details of all the sensors offering thermal data of great importance to you if you want to work on a regional level study or on an urban level study. Band number 10 and 11 in Landsat 8 are thermal bands. They are actually 100 meter but resampled to 30 meters. As you can see, Landsat 7, 60 meter resampled to 30 meters. Band number 6. Same for band for 4 and 5, thematic mapper TM, band number 6, 120 meter actual resampled to 60 meters and 30 meters. Aster has 4 bands, as I said, and others can be used for global area coverage and local area coverage. Local area, again, it is in kilometers, so it cannot be used for urban studies. Then INSAT 3D, 4 kilometer, 8 kilometer cannot be used for urban studies. So there are concepts of thermal inertia, but we are not getting into the detail of that. But we understand that certain materials absorb the heat and retain it. So the retaining property is governed by thermal inertia. So water bodies, rocks, soils will all have different thermal inertia and hence will govern its surface temperature dependent upon the short wave and the long wave radiation. So at night, surface temperature is reversed, water becomes warmer than soil and rocks. Vegetation has a warm signature during night time and a cooler signature compared to the adjacent soil during daytime. So this is a property that is dependent upon the thermal inertia. So for example, you are working on areas like Rajasthan or Gujarat, where sandy soil is there and where deserts are there, then you know that night data is also going to be of help to you and day data is also going to be of help to you. So you can use both the data. If you are not able to procure the data of daytime and nighttime both at a good resolution, you can at least take out and validate with the help of MODIS product. It is going to give you Aqua and Terra data. Aqua nighttime, Terra daytime. So how to process the thermal data? Okay, the thermal data can be processed by various algorithms dependent upon the number of bands available. But four majorly, mainly what we will discuss is mono window algorithm, single channel method, split window algorithm, multi-angle algorithm. Multi-angle algorithm has not been explored so far much. As I told you that emissivity is dependent upon the field of view and the angle from which the particle is being viewed. So this way multi-angle algorithm is also of use. Mono window algorithm as the name suggests and single channel method as the name suggests, only one band can be used at a time. Split window algorithm method, split window as the name suggests, two bands are used and split window algorithm can be used. At this juncture, I'll tell you that various people have developed various algorithms: Rosenstein, Mao, Sobrino, Quinn et al.'s mono window algorithm, then Gymnus Munus Sobrino's algorithm. Mao, I told you, Rosenstein, I have told you. So likewise, radiative transfer models are there. So I have told you a number of examples, and all these have different parameters ingested into it. So if you have to go for a very well validated result, you have to go for a good algorithm where all parameters like emissivity, transmissivity, water vapor, ambient air temperature, surface air temperature, everything has to be made as an input. But the most common of all I will discuss. Okay, I used the term radiative transfer. For energy budget, radiative transfer is going to be of help. Radiative transfer, what are we saying in radiative transfer? That the radiance values received in the thermal region of the electromagnetic spectrum at a sensor, they are divided into three parts: the surface emission, atmospherically emitted downwelled radiance, and atmospheric emission. So there are three things. Surface is involved, atmosphere is involved, then the upwelling radiance and the downwelling radiance is involved. So all these four parameters are involved within the radiative transfer algorithm. We were discussing about emissivity. So what are the various emissivity values of common materials? I said the emissivity for water body, I told you about distilled water, it will be 0.99. Water body, it will be 0.989. And for waste or bare soil, it will be the least 0.896. When I inserted the materials also, for example, tin shades and others, the value came down to 0.1 and 0.2 as well. We have already discussed this in the previous slide. So emissivity calculation is done with the help of proportional vegetation and the emissivity values of vegetation pure pixel, soil pure pixel. So how are we going to calculate? So emissivity is dependent upon the emissivity value of V, that is vegetation, and proportional vegetation. How we are going to take out proportional vegetation and how we are going to take out NDVI, that we will discuss in the later slide. So proportional vegetation is important for calculating the emissivity. DE, that is differential emissivity, and it is dependent upon a very small fraction of the surface property or the shape property of the material that is into consideration. So now let us come to the method by which land surface temperature can be estimated. We have to calculate NDVI and proportional vegetation, number one. Now this all we are doing for calculation of emissivity. Emissivity can be calculated by various methods. Number one method is that you calculate NDVI based emissivity calculation, NDEM, MBEM. So NDVI based emissivity calculation mein you are going to calculate the emissivity with the help of NDVI and proportional vegetation. Second option is that you calculate the NDVI, you calculate the emissivity by classifying the area under consideration. So after classifying the area, you know about the areas and you know from the chart what is the emissivity value. So you fill in the emissivity values and replace the cover with the emissivity value. So in general, we use NDVI based method. So we are going to use the same. How is NDVI calculated and what is NDVI? Okay, NDVI is normalized differential vegetation index. It tells you, it varies from -1 to +1 and it tells you the percentage of greenness. So more the NDVI, more the greenness. So NDVI we are going to calculate by the formula NIR minus R upon NIR plus R. NIR is the near infrared band, R is the red band, and the same in the denominator as well. Proportional vegetation. Now, proportional vegetation is what proportion of vegetation is present. So that can be calculated using this formula NDVI minus NDVI min. Min means the minimum NDVI value divided by NDVI max minus NDVI min. Maximum NDVI value minus minimum NDVI value whole square. So proportional vegetation can be estimated like this. When NDVI and proportional vegetation have been found out, we can take out the emissivity, which for thermal band 6 in Landsat 457, the formula used is 0.004 PV plus 0.986. How we have arrived at this equation, I have already discussed. Emissivity is dependent upon the EV and ES, that is vegetation emissivity and soil emissivity. So taking that into consideration, we have arrived at this formula. This formula can be used for the calculation. The third step is land surface temperature estimation is conversion of dN to radians. Now dN to radians can be converted with the help of the several parameters that are given in the metadata file of the data that you download. So for example, if you are downloading Landsat 5 data, along with it all the bands come and a metadata file comes. So metadata file contains the Lmax and Lmin values. What is Lmax, Lmin? The spectral radiance. QCalmax and QCalmin, that is the quantized calibration value. So if it is 8-bit, it will be 255 and 1. That is 256, total 256. So the maximum value will be 255 and the minimum value will be 1. I hope you are following. Then the last step will be the land surface temperature estimation. So the surface temperature can be estimated taking two things, dependent upon two things. One is emissivity and the other is L lambda, which we have the radiance value which we have calculated in the previous slide. K1 and K2 are calibration constants. They are dependent upon the sensor that you are using. So for example, if you are using Landsat 5, K1 and K2 will be different. Here we have taken the values for Landsat 5. For Landsat 7, it will be different. For Landsat 8, the calibration coefficient parameters will be different. And why we have done -273? Because we have to convert Kelvin to Celsius. So we will quickly discuss a case study now. The case study area that was taken up for the calculation of land surface temperature was Jaipur. Jaipur is a very interesting city and it has certain different characters. So we have already discussed about urban heat island effect. So let us see what is happening in Jaipur. It may be the same, it may be starkly different. So we are discussing about Jaipur, which is the 10th largest city in India. We all know that it was a walled city earlier and has local materials used for the construction of Jaipur city. The percentage growth was 35% approximately, and has approximately 950 square kilometer of master plan area, has semi-arid climate, very low humidity during months like May, June. The relative humidity and the rainfall pattern is so different that you cannot imagine a rainfall lesser than 18 millimeters in this area in the month of May. Soil type sandy loamy and loamy sand within the Jaipur city. And why we have done all this? Because we wanted to understand the area and the character of the surface. So before starting with any exploration, because only then can we relate and understand that why the surface temperature has come this much over this area and why it is different on the other area. So what was the data used? We have used Landsat 5 TM data for both the years 1993 and 2011. Okay, and the data was of May, 26 May and 31st May. But one question may arise that why are we using such a huge gap between the 2 years? Yes, we are using two time periods, and there is a difference in these two time periods. We are using this because we wanted to know that in 20 years approximately, what is the change in the surface temperature? Obviously, if you recall my last lecture when we were talking about land use land cover classification, we have not we have tried to understand that cities do not grow overnight. Cities take time to grow, and a predominant increase can be seen only after a decade. But this is climate and we're talking about temperature. So, and we relate to urban heat island effect. So when we are saying that, we are saying that the urban areas are expanding, and within 2 decades it must have expanded a lot, and hence we can see a starkly different scenario between these 2 years, and a huge difference of 20 years. We could have taken more also, but data was a difficulty, so we took the maximum we could, and it's a period of 18 years or so. USGS website, download the data. So the methodology that we adopted was that we had the satellite data for 1993 and 2011. We did the land use land cover classification because we want to relate the land uses with the surface temperature. So we did the land use land cover classification and accuracy assessment and change detection for both the years 1993 and 2011. Simultaneously, we took the satellite data, we took out emissivity through the NDVI, and we took out brightness temperature through radiance, and we calculated the LST, that is the land surface temperature. I'm saying method 1 because we use the normal method. In the second method, we have used Quinn et al.'s mono window algorithm also, which I have not discussed in these slides due to paucity of time. And then we have related the surface temperature with the land use land cover classification. So this was the land use land cover map for the city of Jaipur. Oh, Jaipur is a pink city, yes. 6 classes: agriculture, barren and sandy, built up, fallow land, forest, water bodies for both the years 93 and 2011. First, we wanted to analyze land uses change, which we had already done, not put here. Then land use, land cover, and the LST. Now on the right you have the land surface temperature. Now land surface temperature, blue in color is the coolest, and red in color is the heated up area. And I have given an interval of 4 degrees Celsius in this, and have tried to maintain the same degree difference for both the years, that is for 1993 also and for 2011 also. However, the minimum and maximum may vary, but I've tried to keep lowest and highest of the similar range and similar intervals, so that the same area can be related, that yes, this area was 26 degree and in 2011 this area has become 27 degree. Okay, so startlingly, we can see something that the urban areas have lesser temperature than the outside areas. So, oops, we are not seeing any urban heat island effect. So, this is drastically changed pattern. But believe me, we are talking about Jaipur, the month of May, and we are talking about a situation which generally does not exist in other composite areas. 31st May 2011, same Jaipur, lot of urban area, but as compared to the surrounding bare soil areas and the fallow land areas, the temperature of the urban area is lesser. This is the same image of land surface temperature, only we have tried to give a grade from low to high, and you can see that the urban areas have lesser temperature, the adjoining areas have more temperature, and we have tried to relate it with MODIS data also. So MODIS data can be downloaded, as I said, USGS website, MODIS, Aqua and Terra data. This is the Terra data. 1 kilometer grid spacing. So we tried to analyze and see the change in the land surface temperature from 1993 to 2011, and we could see that in fallow land the average change is very high, 4.68 degrees Celsius. In built up it is very high, 3.58 degrees Celsius. In barren land also it is very high, 3.65 degrees Celsius. So if we plot a graph and we try to analyze that, yes, there has been a difference. So we see that barren land, fallow land and built up have a huge um, temperature increase in 2011. So blue line is showing you the temperature in 1993. However, 2011, the red line shows you the temperature increase. Now, if you can clearly see that the difference of temperature within the urban, that is the built up, is very high, and in the fallow and in the barren also it is very high. So the change is very high. So that means that the the, the hotter areas are becoming even hotter with the years and more built up. So the temperature, the average temperature was lesser in 1993, but the average temperature has risen in 2011. Now this, my dear, can be considered to be an indication towards what? Some change in the climatic pattern. Alright, so we have various thermal applications, and to conclude I would say that not only in the urban areas but also for the identification of geological units and structures, for soil moisture studies, for hydrology, coastal zoning studies, volcanology, seismology, forest fires, environmental modeling, meteorology, military applications, heat loss from buildings, all these have applications with the help of thermal remote sensing. So with this, I take now ready for the questions, and